The magnetic field of the moon could be 2 billion years old. Two mechanisms may have driven the moon's primordial churning, according to new studies from MIT, extending the lunar dynamo's duration by at least 1 billion years. An active dynamo once churned within the moon's molten metallic core, generating a magnetic field that lasted at least 1 billion years longer than previously imagined, according to new evidence from ancient lunar rocks. The churning of conducting fluids within many stars and planets powers dynamos, which are natural generators of magnetic fields surrounding terrestrial bodies. The same researchers discovered 4 billion-year-old lunar rocks that originated under a much stronger field of approximately 100 microtesla a few years ago, and they determined that the field's strength declined drastically around 3 billion years ago. The researchers were unsure at the time whether the moon's dynamo, the associated magnetic field, went out quickly or persisted in a feeble state before disappearing totally. The findings point to two possible mechanisms, one that may have powered an earlier, much more powerful dynamo, and another that maintained the moon's core simmering at a much slower boil at the end of its life. Weiss states, the concept of a planetary magnetic field produced by circulating liquid metal is actually only a few decades old. Scientists have discovered that some of the rocks carried back by NASA's Apollo astronauts from the lunar surface are reliable recorders of the moon's ancient magnetic field. Scientists can use these grains to calculate the intensity of the moon's primordial field. The trouble is that there are very few lunar rocks that are younger than roughly 3 billion years old, Weiss continues. This is because the moon cooled about that time, volcanism basically stopped, and with it, the development of new igneous rocks on the lunar surface. However, there is a tiny group of rocks returned from the Apollo missions that were created not by early lunar eruptions, but by asteroid strikes later in the moon's history. The heat of such hits melted the rocks, which recrystallized in orientations defined by the moon's magnetic field. Weiss and his colleagues examined Apollo 15 sample 15,498, which was obtained on August 1, 1971, from the moon's dune crater's southern rim. The sample is made up of minerals and rock fragments that have been welded together by a glassy matrix, the grains of which contain recording of the moon's magnetic field at the moment the rock was put together. You compare that field to the natural magnetic field you measured beforehand, and from there you can figure out what the ancient field strength was, Weiss explains. We have finally achieved an accurate measurement of the lunar field in this method, Weiss explains. Weiss and his colleagues believe that the moon's dynamo may have been driven by two different causes because of the steep decrease. Around 3 billion years ago, the moon may have drifted far enough away from the Earth that the power supplied for the dynamo through this mechanism became insufficient. This coincides with a decrease in the strength of the moon's magnetic field. The moon's core most likely maintained a low boil as it migrated away from the Earth, cooling slowly over at least 1 billion years. As the moon cools, its core behaves like a lava lamp, Weiss explains. Low-density material rises because it's hot or because its composition differs from that of the surrounding fluid. The researchers intend to examine even younger lunar rocks in order to identify when the dynamo entirely died out.
Thank you for watching Mariaki. Gives us a like and subscribe please.